Hello everybody. So today we talk about the physics of bipolar transistor and the MOS transistor. It's a very basic stuff. Once you know it, then you can go on to the circuit design. Without this, if you try to do circuit design, often you wonder why you make a circuit this way or other way around. It's a very basic stuff. If you keep it in your mind, then you understand why people design the circuit in such a way that you will probably understand the reason. Okay, first of all, we talk about bipolar transistor. As you know, you have two type. This is NPN and this is a PNP, right? The MOS, you have gate, source, drain, and N channel, and P channel. Okay, so since N channel, the substrate is I show you the structure later. The substrate is N type, so it's going against the P type. You can indicate like that. So let's talk about the structure. Why this way? Okay. We talk about NPN here because it's same as PNP. It just switched the polarity. Now we call this collector, emitter, and the base, right? And NPN, you have N, P, N, but actually it's created this way. This is a substrate. You create P well and high impurity dose. This become E, and this become base. And the corrector, you need a deep and implanted N plus. So the P layer here is sandwiched. This is a P plus actually. The substrate is actually this isolated. Each transistor is isolated by the oxidized silicon. So you oxide the both side isolated, and the substrate is P, and that's what it is. This is the active area. Active area, physically active area is this area, the current. So it's a kind of sandwich structure, and base voltage VBE is positive, and this part current flow like a diode, right? Then you also apply collector voltage. This is VCE. Okay, so here's a depletion area because you apply positive voltage to N, and since this node is higher, this dominate. So all the electricity, the electrons are depleted here, and you have a bunch of hole plus charge here. So because of that, this ICE is almost zero, right? So we talk about effect of applying a voltage here in the base. This going to inject a lot of hole. Actually, in this case, electron is injected here to fill in all the holes, and this electron some charge here and fill up this area. So it's become like a lot of carrier added to the depletion area. So suddenly this current start flowing. Okay. So you remember that the VBE, this diode current effect is VE equals some kind of base current E QVBE over KT minus 1. Okay, remember this is important. And once sufficient carrier is injected here, then this becomes like a conductor. So ICE start flowing. So the ratio between this current IB and this entire current IE, okay, not the ratio of this is let's see, I see the correct current, the component of IE is IB base current and the corrector current. The corrector current, how much is a ratio? This is called alpha, right? And the ratio between the IB and IE, IE over IB is called beta. Okay, so this is called transistor beta, used for design. It's about 100. A lot of transistors depend on the doping of the impurity value change. The relationship is obviously 1 minus alpha 1. So alpha is 0.99, means most of the current, because when transistor turn on, most of the current come from here. So this alpha is 0.99. Most of this entire current is 99% come from here. The base current is very little, 1%. Okay, so that's why it can do amplification. Suppose IB is 10 microamp, then 100 times IE is 1 milliamp. Okay, so any signal you apply, IE is going to be 100 times larger current. So bipolar transistor is a current amplification. Now, this is important. ICE, apply the voltage, the current, how much current is flow, and this is the voltage CE. What's happened is, remember this equation, the exponential equation. It's follow the base emitter diode current, and once it's become the conductor, simple conductors, and it's saturate at certain base level. And if you increase the base level, saturation point is higher. So IB 10 microamp. This is the base emitter current. It's flowing the diode portion of the transistor. Okay, it's affect voltage. Remember, this is a very important curve for transistor. ICE. This is ICE voltage, and VCE, this is a VCE. So it shows the switching. Once it's switch this much current, which is 100 microamp, 500 microamp, 1 milliamp. So transistor flow this much current depends on this IB. This is the IB. So IB control saturation current. Okay, so that's why we write the ICE. Actually, this is IE, is the basic current, right? You have to do beta times I0 and QBE over KT, and -1. We can ignore this because this part is high when it's saturating. This curve is basically exponent this part. Okay, so this give the current. This give the IB, and times beta is going to be IE. Okay, so this is the transistor's basic equation. It's exponential by VBE, but this VBE actually generate IB. So whenever you design the bipolar transistor, you look at the IB current and estimate IB current, then you know pretty much the current on the collector side. Okay. MOS is different. MOS structure is, say, you make a P well and N plus, and you put the insulation oxide silicon and put the gate, and either one can be drain and source. We call that source voltage, drain voltage, and this is gate voltage, right? So if you do this, what happens is when you apply voltage between source on drain, there is a depletion layer. This area will be depleted because this is NP, this is reverse polarity. So this is depleted completely and current doesn't flow. But this gate can change this situation. What the gate does is, when VG become larger than certain voltage, we call threshold voltage, right? Then it start having a little bit inversion layer. And what the inversion layer is, because of this voltage, positive, electron is attracted, and this change to N type. The substrate is B type, okay? And this entire substrate is N type. So that's why this P well, the voltage applied can never leak out to the substrate. Now, this inversion layer is channel, N-type channel is created, okay, and start having a current flow through. Not much, okay. Once you increase this voltage, then this inversion layer stretch out all the way and reach, and it become N channel is created. So what happened is, there is a threshold voltage, okay, but the drain current is going to be some constant and depend on the width of the gate and length of the gate, Vg minus Vt. Beyond threshold, this square, okay, this gate voltage reach beyond Vt is start having an inversion layer, and the inversion layer grow as Vg increase, and once this inversion rate reach, then it's saturate, just like this one. It's become like conductors and constant current. So actually, we can have a similar curve as the bipolar transistor. This is, in this case, we call channel current, and this is drain voltage. Well, the source voltage, whichever you call the drain and the source, the voltage, this square, there will be, once current start flowing, it's follow this one until it's saturate. Once it's saturate, and saturation depend on Vg minus Vt, right? Actually, Vt depend on the impurity levels. You can just in the MOS circuit about 3.5 volt. So beyond 3.5 volt Vg, this we can we can put this one beyond threshold voltage, VG1, VG2, VG3, saturation current change. Okay, so if you compare with bipolar, this is not the current IB, so this is the voltage amplification, because there's no current for gate. This is the capacitor, basically, capacitor. And VGE just apply the electrical field in the bulk, in this case N-channel MOS, and affect the surface, of this P well, create inversion N-channel, and once N-channel reach to the other side, okay, then IC start flowing, this current start flowing. That's a different color. How about this one? This way. Okay, so that's the IC here. There's 3 different current level, depend on the BG, the gate current. So gate current, gate voltage controlled IC. Okay, bipolar, base current control the IE, the current flowing through the device. Okay, this IC essentially same as ID and VG. VG control saturation current, saturation. Okay, before it's saturate, this, remember, this is a square VG minus VT square curve. Okay, before saturation, it's follow this square. The bipolar, it's follow exponent, KV base voltage KT. This is the QB over KT, exponent curve. This is square. So remember, here's the difference. And sometimes this difference is important for circuit design, especially in analog design. So you have to remember this basic. So MOS, this same as the N channel and the P channel. The P channel, this voltage becomes a BG. P channel, this voltage becomes a VG. Because of structure, the nature, you have P, and N well. Okay? So you think about it, how create the inversion rate. If you apply positive, it's not inversion, it's immediately flow the current here. You have to apply the negative. Okay, negative from this source point. You apply negative voltage from the source point, then depletion layer is created and inversion start here, and the current start increasing until this inversion layer reach to the another point, then from there it's become like conductor and saturation. Okay. Another important thing is, a lot of people don't mention this in the transistor operation. Saturation is actually, it's not constant, it's slightly increased. And this is important in analog circuit design. Okay. If you increase the voltage across this transistor, even IB is fixed, is slightly increased. Saturation is not actually constant. Okay. There are various physical effects. This one too. This increase by secondary effect of the device. So it's not perfect constant current. It's slightly, the current increase when you increase this voltage. Even VG voltage is the same. Okay. Digital design, the 0-1 type of digital design, you don't care because you don't operate by this slight difference in the current. You just operate on or off, right? So that's the depend on what you do. The analog design, you always need to know this secondary effect is going to change the analog circuit design. The digital design, it's become just it's buried into the details because you care only on and off. But on and off, digital design, you have this transition time, and sometimes secondary effect affect this transition time. The switching speed become very slow. When you talk about digital circuit switching speed, it's become analog circuit design, no longer digital. Digital, ideally you want to have on, off, ignore this switching speed. But a lot of digital design, the switching speed becomes the issue. And this switching speed, you need analog level design. Okay, so that's all for today. The semiconductor is the interest on semiconductor is becoming less and less in the United States because industry is shrinking, but still important to have this basic knowledge in order to do the circuit design. And besides the circuit design, you need to have the logical design is like a programming, but you still need the circuit design knowledge, because like fan in, fan out, the how many you can drive, how many logic you can drive. It's ideally one signal can drive as many gates as possible, but physically it's impossible. How do you deal with that? And also I/O circuit. Well, somebody designed I/O circuit, right, and put it in the library, so logic designer just use it. But sometimes the chip requirement and each pin output characteristic, there is a requirement, and how do you select those? You need a basic knowledge of the circuit level, physics level understanding. Okay, I think that's for today. If you like it, please subscribe and click like. We'll see you next video.